everyone. Today I would like to try to stay at the back of the classroom, as possible as I can, because I want to encourage study of students. So maybe we can read a little bit about what is critical logic, because we are going to talk about what is. So could you tell me what is critical logic? What's the no idea. What, what is critical logic? Okay, if you don't remember the definition of critical logic again, it will be so difficult for section 1.5 because we are going to introduce the more complicated form of critical logic. So, anyone can summarize critical logic for me? One point. I'll ask you. Critical logic. Um, so we have three different parts. Do you get the part of logic? Three different parts. So we have variables, we have predicate, and we have quantifiers. Variables are linear positional variables with x1z, and one is the representatives. Practical logic, we call that predicate. Alright? And then most importantly, we have quantifiers. Remember, for all and for some, we need to define what is the range of all of these elements we are trying to describe. So let's see. Today, next is quantifiers. Okay, so I need the remote control so that I can walk around in the classroom. Okay, let's see how far I can go. Okay, today, let's see a summary of our lecture. We have basic quantifiers and very important thing is the order of quantifiers. And then we will see different examples how to translate new sentence to nested quantifiers and vice versa. And last thing is into nested quantifiers. So let's see what is nested quantifiers. Okay, if you see two more quantifiers, then we call them nested quantifiers. In this example, every real number has an inverse. We have introduced the inverse, right? What's inverse for real numbers? How about you? What is inverse of a real number? A real number. No. Choose an imaginary number. Okay. The inverse of a real number is x plus y, and we take a particular y to make x plus y equals 0. Then we call that the inverse for the element x. Okay, we have a real number x, and you can find another real number, x plus Okay, so let's see this example. Every real number has a particular number as its inverse. So we have for all x, we can enumerate all numbers within the range of real numbers. Then exists a particular y that makes x plus y equals 0 true. Then we can claim every real number has a inverse. Okay, so this is a very simple sentence, but for its practical logic, we can see we have two quantifiers for all x and for some y. Okay, so we call this nested quantifiers. Next, I would like to include one important concept because it will help you solve the other problems of nested quantifiers easily. Okay. Next, you need to consider nested quantifiers for all x, q of x. And what is q of x? For some y, p of x, y. Okay, you can separate your original terminology into parts. If you consider this part is q of x, then it will be easy. That will be for all x q of x. Let's go back to simple form of comparison. Right? Then if you examine q of x closely, then you will see that's for some y, p of x, y. And remember this because we will apply this to a lot in the following questions. Okay, so next let's see how we consider nested quantifiers. Because you may have 3 or more quantifiers for all x, for some y, and for some p, maybe for some r. Okay, so this one will be very complicated. How do you think of if the methodology is true or not? Okay, so we just follow the similar ideas. Methodology. If we have for all x for all y, okay, that means you need to examine every element within the domain to see if for all x, q of x is true or not. In this case, q of x is for all y, p of x, y is true. Okay, so suppose you select one element x, and then you need to examine for all y if p of y is true. Okay, then you look all elements within the domain of y. Once you discover for a particular y, p of y is false, then for all x, p of x, y is false. If it goes well, then you enumerate all y within the domain. And we make sure that particular x is okay. And then you jump to the next element of x. After you examine all elements of x within the range, then it's all okay. Then we can for all x, for all y, p of x, y is true. Okay? So please translate what I said in Chinese for everyone. How about you? How to make sure for all x for y, p of y is true? Anyone understand? How about you? Please speak in Chinese. Explain the concept right now. Okay, but very close. Okay, so maybe I speak a little bit slowly. We want to know for all x for all y, p of x, y is true. or not. Then within the domain, we have all elements, right? Within the domain. Okay, then we select one element in this domain. For example, we need to make sure for all x, Q of x is true, right? So the thing we need to make sure is if every x within the domain that Q of x is true. So we need to examine the element one by one within the range. So if we call this 1, P2, P3, we have used P1, P2, P3 to P100, for example. Okay, then we choose D1 as our target. Then we examine if D1 to other y within the domain if P of xy is true. So how we examine? So maybe we need to examine if we have the same domain, then we need to examine P of D1 is true or not. P of D1 and D2 is true or not. P of D1 to D100. If these terms are all true, if you discover any pair of D1 or D something is false, then this particular logic is false. Because it's not true for all x p of y, for all y, p of x y is true. Okay? Then what happens if it passed the test? D1, 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 D2, D1, D100, all this particular logic is true. Once it is true, then we jump to next element. Then our target is select as D2, the second element. And then we examine D2, D1, D2, D2, D2 to D100 to see if all of them are correct. Once you examine to the next element, 100, then if D100, D1, D100, D100, all of this particular logic is true, then we can claim for all x, for all y, P of x, y is true. During the process, if you can find any pair is false, then the practical logic is false. Okay. So follow the same idea, you can see how we examine for all x for some y. So for all x for some y, we change the quantifiers to y. Then we follow the same idea for all x p of x, and we select the first element d1. Okay, and we examine d1, 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 d2 to d1, d100. If any one is true, for example, d1, d2 is true, then we find the particular element for some y that for this element, p of this element y is true. Then it passes. Okay. Then we can jump to next element for d2 to see if we can find some particular element to make p of x y is true. And we loop until d100. If all elements pass the test Q of x, then for all x for some y, P of x is true. Okay. Okay, next let's see the order of the quantifiers. P of x, y is the same as x plus y equals y plus x. Then we have for all x for all y, P of x, y. That has the same truth value as for all y for all x, P of x, y. If you can follow the same procedure, then you can verify they are true, because once you examine the target x1 is 2 to see qx1, qx2 is true or not, then once you choose from y, you choose y1, and then you choose different x1 to x100, you can see the results remains the same. Okay, so that means we can switch the quantifiers. But next, let's see the second example. If we have x plus y equals 0, and u is the real number, then for all x for some y, p of x, y is true, right? Because we are trying to discover the inverse of x. So for all real numbers, its inverse is this. So x plus y is 0. This tells you it's true. However, if we switch the order for some y for all x, let's see what happens. Can we find a particular unknown y, then y plus all x is 0. All x is all real numbers. So we have a particular real numbers, then plus all real numbers. No matter what we choose, that's y is 0. Okay, notice such y is not exist. So why not if you switch the order of this methodology, then the truth value changes. Okay, this tells us you cannot switch its order arbitrarily. Okay, sometimes the meaning remains, sometimes it changes. Okay, next let's see the example. If we have p of xy, that is x dot y, x times y is equals 0. Okay, it's not plus, it's x times y. Okay, then what's the truth value of the following example? If the domain is real number for all x for all y, p of xy. So let's see, let's choose the first element, for example, 1. Okay, so if x is 1, then we have 1 times all real numbers is 0. Okay, of course not. Okay, so you cannot find any, for all x means that all real numbers times all real numbers is 0. Of course it's false. For all x for some y, so take x as 1 for example. Can you find a particular y that makes 1 times its number is 0? Yes, right? So how about we're trying different real numbers? How about x is minus 6? Can you find a y minus 6 times something is 0? Yes, because if you choose y as 0, then you can always make this equation true. Okay, so this is true. Then, how about we switch the quantifiers for some x for y? Can we find a particular x within the domain of real numbers that times all real numbers? What's that number? 0, right? If we choose 0 as x, then we can say for some x, x is 0, and it times all real numbers y to make it 0. Okay, then you can verify the last example by yourself. Okay, so we know how we loop within nested quantifiers to determine it's true or false. Okay, so we have the following tables. So maybe I invite someone to explain for some x or y of x, y, how to confirm when the truth value is true, how you apply this process to make it true. Okay, in Chinese. We have a table for given statement. For some conditions, it will be true, for the others, it will be false. How to make this true? How you apply this process to exam for some x for y, p of x, y is true. 如何让它为真？
哦，在就是那个会对说得来，然后
这是这个 predicated logic 的意义嘛？那你如何用这个方式检查，确保这个是对的？Okay. Alright, so this is for some x for y. So how we exemplify these two loops? Okay, firstly, you select the first element x1. And then you need to make sure for all y, p of x1 is true. So after you choose x1, then you test all y. In this problem, we have d1, d2 to d1, d100. Okay, if they all pass the test for all y, this 100 predicated logic is all true, then that's it. Because we find that particular x that makes all y, p of xy is true. So if we have any predicated logic, for example, p d1 and d100 is false, that means x1 cannot make all y. Then we need to try next element. So next we select the x2. You repeat this process until you find one particular x that for y is true. So the description is we can find a particular x that makes p of xy is true for every y. If you can find that particular element x, then this particular logic is true. Okay, so when we make this false, then we negate this description. So it's not the case there is an x that every one of xy is true. Okay, if you cannot find that x, that means every x you can find out the y that is false. Right? So maybe we will see this later because we are trying to negating the nested quantifiers. Okay, let's give papers to everyone. Okay, next let's see this, how we translate nested quantifiers into English. Okay, so we have for all x, then we have parentheses of x or for some y, c of y and f of x. Okay, so let's see the meaning of this function. C of x as a group, f of xy is in y of friends. Okay, so it's very intuitive. C as a group, f xy are friends. Okay, and then for both xy are all students of our school. Okay, so let's see what this nested quantifiers tells us. Okay, for every student in our school, we have two compound propositions, C of x or the other conditions. Okay, the first condition is C of x. That means for all students in our class, x has a computer. Okay, this is the first condition. Or for some y, C of y has a computer. Y is friends. So that means for all students in our class, either he has a computer or he has a friend who has a computer. Okay, so that's the meaning of this nested quantifiers. Okay, so that means every student in your school has a computer or has a friend who has a computer. All right. Next, let's see more. Let's see for the virus. For some x, for all y, for all z, f of xy means xy is friends, x, z are friends, and x and z y and z are not the same person. Okay, if this is true, then f of y z, that means y and z are not friends. Okay, so we have a particular element x in the domain. The domain is all students in our school. So this one is a very special student because if he has a friend y and z, they are not the same person. Then these two friends are not friends to each other. Okay, and you can see for this particular student, we have for all y and for all z. That means all of his friends, if x and z are, are friends of his husband x, and y and z do not know each other. They are not friends to each other. Okay. So how we write this terminology in a simple English sentence? Right? So 简单的来说呢，就是有一个人，这个人的所有的朋友彼此都不是朋友。好，我们有现在有一个人，那这个人的对于所有的 YZ，要 YZ 是他的朋友，而且 YZ 是不同的，那 YZ 就互为朋友。So simply speaking, it means there is student of whose friends are not friends with each other. None of whose friends are friends with each other. Okay. So, do we have such people, such students? Students do not know each other friends. They are not friends with each other. It's not likely, right? Because all students in this school, we are in the same department, maybe computer science. Then we have one student, two students are not friends with each other. But because everyone is his friends in this classroom, we are the same department, computer science. But we don't have anyone as friends to each other. That's not likely happening, right? Okay, next let's see another example, how we translate English sentence to nested practical logic. Okay, especially we can translate mathematical statements. Okay, so this is very important because next for maybe chapter 2 or chapter 5, a lot of different mathematical equations. Actually, you can try to translate this sentence to nested quantifiers or nested practical logic. Okay, so let's see this example. The sum of two positive integers is always positive. Okay, so you can see this sentence is very easy and it is true if we calculate the addition of two positive integers, then the result is always positive. Okay, so let's see what's behind this sentence. Okay, actually it means for every two integers, if the integers are both positive, then the sum of these integers are also positive. Okay, actually we have conditional statement behind this original English sentence. The sum of two positive integers always positive. That means if we have two integers that are both positive, then the results after addition will be positive. Okay. And then we have hidden quantifiers. Actually, we have for every two integers. Okay. Because once we say the sum of two possible integers, that means we can select arbitrary integers within the pair of integers. Okay, so we have hidden or implied domain of integers. And then we have hidden conditional statement behind this sentence. Okay, so next we can, this is the complete predicate of this original sentence. And we can translate to predicate logic. For all x, for all y, the domain is integers. If x larger than 0 and y larger than 0, these two elements are positive, then x plus y is larger than 0. Alright, next let's see how we translate English into logic expressions. Okay, let's see if a person is female and is a parent, then the person is someone's mother. Okay, because she's female and she is a parent. Okay, then of course she must be someone's mother. Then she can call a parent, right? So next, let's see how we define the predicate logic. The positional function f of x means x is female, so we use f, and p of x is a parent, and this person is someone's mother. Okay, so we use n of x y, that means x is the mother of y. Okay, so that's our positional function. And let's try to convert this sentence to predicate logic. This is the sentence of if something, then something. Then we have the biconditional statement. So let's see. Maybe you need to first distinguish the qualifiers is for all or for some. Because the sentence doesn't say if a person is some properties, then the person will have some properties. Okay, so don't do that. If it's a person, that means for some it's because it says once it follows its properties, then it has some properties. Then for all elements within the domain, it will follow this equation. Okay, so we have for all x, if x is female and x is parent, then for some y, alright, so in this case, we can also move for some y in front of this predicate logic for some x, or for all x for some y, f of x and p of x and f of x y. Okay, next I will tell you how to show that this predicate logic is equivalent. So you will see it's okay if you move for some y in front of this predicate logic. It remains the same meaning. We can verify its equivalent predicate logic. Next, let's see the example to translate from English. Okay, so we have brothers are siblings. So maybe simply we can define the propositional function b of x, y means x, y are brothers, and s of x, y means s are siblings. Okay, so what's the meaning of brothers and siblings? Siblings include brothers and sisters. Okay,
So if that means if x, y are brothers and they are also siblings. Okay, so we have for all x for all y within the domain, if x, y are brothers, then x and y are also siblings.
So next, siblings, simple and symmetric. I and you, we are siblings. You and I are siblings too, right? So if you switch the order of x, y, it's also siblings. And we can have for all x for all y, if x and y are siblings, then y and x are also siblings. Okay, next one, everybody loves somebody. Okay, that means for all people who loves someone. Okay, so maybe we can define L of x, y. That means x loves y. Okay, once we have the propositional function L of x, y, then how we assert everybody loves someone, right? For all x, everybody, and we have for some y exists that x loves y. Okay, if we enumerate all people within the domain, then you can see for all people, then we exist some y that x loves y. We also have there's someone who is loved by everyone. Okay, so he must be very charming, right? So he's loved by everyone. So we exist some y for all x that x loves y. Then he's the lucky one, exists y. There is someone who loves someone. Okay, so very good. They will get married soon because they. So we have for some x, for some y, that x loves y. And everyone loves himself. That means everyone is narcissist. Okay, he's the one who's sitting by the crowd and sees the people's flowers. Maybe he's the flowers. Okay, so everyone loves himself for all x, all of x. Okay, for everyone, that x loves x.
Okay, lastly, let's see how we negate nested quantifiers. Actually, we can apply very similar concept by De Morgan's law. Okay, so if we have our previous example, if a person is a female and is a parent, then this person is someone's mother, we already have for all x of y, female and parent, he is mother of y. Once we want to negate this logic, then we have the condition. We have the connective set in front of this logic. That means it's not the case if a person is a female and parent, then he is mother. Okay, so next we can apply the Moore's law to rewrite the original practical logic step by step and see what is its equivalent form. So remember, once we have the negation in front of this particular logic, then we can distribute this negation to every term of this particular logic. So for all x becomes for some x, for some y becomes not for some y, that means for all y. And then we have not this parenthesis. So we need to rewrite the logical within parentheses. We have the conditional statement if P then Q. So that means we have the equivalent form. If P then Q is equivalent to not P or Q. Okay, so we can write not P or Q. Okay, so this is how we write conditional statement. So once we have the negation in front of these parentheses, then we have not and not f of x, y. So if you remember double negation loss, that means not this parenthesis means p of x and f of x. And then we have n not f of x, y. Okay, so in the end, we have two conjunctions. The first two have a parentheses, but you know the parentheses will be removed because they are all elements of conjunction. So we can choose who have them first. Okay, so in the end, we have for some x or y, uh, equivalent nested functions to the original sentence. It's the negation of the original sentence. Okay, so let's see. What's the English sentence of the last one? Okay, why is the negation of the original sentence? Okay, if we have a particular person X, then for all persons in the range, then X is female, X is parents, and he is not everyone's mother, or she is not everyone's mother. Then this is the negation of the original sentence. If a person is female and parents, he must be someone's mother. But now we have a particular person. This person is female and parents, but he's not everyone, she's not everyone's mother. Not any of X, Y. Okay, so that's the definition of the original nested functions. All right, next let's see the order of quantifiers. How about switch the order of quantifiers for all x for all y, p of x, y. So we already say that it's equivalent to for all y for all x, p of x, y. Because based on the process, we have two loops to examine every element. If for all x for all y, p of x, y is true, then once you choose y and examine all x, the results remains the same. Okay, and we already see for all x for some y, you cannot switch the order to for some y for all x, p of y is true. Once you use the example of inverse, then you could false. Okay, next we want to discuss if we can distribute quantifiers to logic connectives. For example, we mentioned that the importance of these parentheses because we want to assert for all x, x has the property p of x and another property q of x. Okay, so for all x, it has the property p of x and q of x. Does that equivalent to for all x p of x and for all x q of x? So let's see what's the meaning of this one. That means for all x p of x is true, if x is the domain, it's the element of the domain. And then in this domain, all x also has the property q of x. Does that have the same meaning to the first one? Right? Because you can extend every element. The first element, it has the property p of x and q of x. The second element has p of x and q of x. That means every element you can extend has property of p of x, and it also has the property of q of x. So they are two equivalent forms let's see the second one. For all x, if p of x is true and q of x is true, does that equivalent to for all x p of x and for all x q of x? Okay, please write the Venn diagram of these two to compare if they have the same meaning. And I will invite someone to draw the Venn diagram for us. So if you consider P of x is one particular property of x, and Q of x is another property. Okay, maybe I draw the left-hand side, then you can draw the right-hand side. Okay. So this is the domain of x. Okay, so we have a lot of different elements within the domain. For example, x1, x2 to x100. Then it tells us if p of x is true, that means for some x, it follows the properties. So maybe we can have a circle here. That means the x within the circle, p of x. That means x has such properties. If it has such properties, then q of x is also true. Then these four elements also okay, so we can draw the Venn diagram like this if we consider the set. Okay, and we have the universal set for all elements. We have, for example, 10 elements. But if x has the properties, then it has the property of Q. So in this case, we have 10 elements. If we have these four elements, P of x is true, then these four elements, Q of x is true. Okay, that's the Venn diagram of the left-hand side. What's the Venn diagram of the right-hand side? One extra point if you draw the Venn diagram correctly. Anyone? Maybe you try to draw something for us.要画要画啊！你会画在第二个图里面哦。Okay, very good. So the meaning of the right-hand side is we have the domain for all x. So if for all x p of x, that means all x has the property. So we have 10 elements, right? If we have 10 elements for all x p of x is true, then that means 10 elements has the property p of x. Then for all x q of x is also true. That means for these 10 elements, if all of x p of x is true, then q of x is also true for all elements. So that means we have 10 elements here. These 10 elements has the property p of x and q of x. So you can see these two Venn diagram does not equal, right? have different meaning for these two predicate logic. All right, maybe we can try some real sentence. So if P of X the student is tall, Q of X means X is rich. So we always say tall, rich, and handsome, right? Okay, so if he is tall, then he's rich. Okay, so for all students in our class, for example, if the student is tall, then he's rich. So how about this one? Please write down your answer in your paper. Okay, so maybe we can consider the second side in our class. So if the definition of tall is taller than 100 centimeters, okay. So if the person is tall, then this person is rich. Okay, he has a saving for like more than 1,000 USD dollars. Okay. Then what's the sentence of the right hand side? Please read your answers to that one.
All students are tall
That's right. So this means if all students in our class is tall, the height is over 180 centimeters, then all students are rich. Okay. So you can see if I ask them stay up, if it follows this condition, then maybe the student over 180 centimeters will stay up. That means this person is rich. Okay. But the right hand side means if everyone in our class is tall, then everyone is rich. So you can see these two methodologies have different meanings. Okay, so that's the end of section 1.5. All right. Any question for this section? We can repeat in Chinese again. All right. So next, the quantifiers and the importance of the orders of quantifiers. And we have several examples to translate from nested quantifiers to English sentence and translate English sentence to nested quantifiers. And also the mathematical equations. We can also to nested quantifiers. And then we are trying to define what's the negation of nested quantifiers. All right, so maybe we can try the last example because we have a very weird sentence here. Okay, let's say this sentence. There is a student, none of whose friends are friends with each other. Okay, try to negate this sentence. What's the negation of this sentence? Because this is a very weird situation, a very weird sentence. There is a student, none of whose friends are friends with each other. What's the negation of this sentence? Don't simply write it's not the case. Write its real meanings. 好，那我们先用中文确定一下它的意义好了哈。假设有一个人，他所有的朋友两两都不会是朋友，那这句话的否定应该是什么？是什么？有一个人，这个人的所有的朋友都互为不是朋友，这句话否定应该是什么？没有这样的人。好，那没有什么样的人？OK，那如果用正面的句子来描述这件事情，它会变成一个什么状况？我们怎么用正面的句子来描述这个情形？再讲一次。OK， 所以你的否面是否定，就是否定后面这句话。那你怎么没有想否定前面这句话？这里有一个人，所以后面是所有人都不是什么情形。Alright, so maybe we can start from the Morgan's law first. How to negate this particular logic? Maybe we can, once we have the negation of the original particular logic, then we can see how to translate the particular logic into English sentences. Okay, so please write your second answer, the result of negation of this statement. Alright, so we have not for some x for all y for all z, and if f of x y and f of x z and y does not equal z, then not f of y z. Okay, so remember when we apply the Morgan's law to this particular logic, we need to rewrite the conditional statement first. Then we can apply how this equation changes these terms. Okay, so remember we have if P then Q, that's equivalent to not P or Q. So we have not of very large parentheses, f of x, y, and f of x, z, and y is not p or q, okay, or not f of okay, so that's the equivalent form. So next we can apply the Morgan's law to this sentence. Alright, so we have the equivalent form, not for some x, so we have for all x. Then we have not for all y, and we have for some y, for some z. And then negate this parenthesis. Okay, so we have not parenthesis or something. So not this parenthesis, that means we have both fxy and fxz, and y does not equal z. Okay, and then when we apply negation into this parenthesis, Firstly, we negate the first term, then we transform over to n, and then negate the last term. So it will be f, y, and z. Okay, so you can see we have 4 terms, they all end together. So let's see what happened for the negation. We have for all x, for some y, for some z, x, y are friends, x, z are friends, they are not the same person, and they are friends. Okay, so you can see for all x, you can check for all x, q of x is true. If you consider this one as q of x, then you can examine every person that the following practical logic q of x is true. So what is true for everyone? Exists x, exists y, x are friends of x, x friends are y, and x and z are friends. They are not the same person. And y, z are friends. So that means for everyone, they must have a pair of friends. They are friends too. Right? Okay, so that's the negation of the original sentence. So what's the Chinese sentence for this English sentence? Okay, can you try it again? 如果是中文的话，这个句子讲的是什么？嗯嗯，对。那假设不要用 variable， 还是只用中文，你要怎么讲？啊，这还不够完整哦。好，所有的学生的朋友，所有的学生里面，每一个人的朋友里面至少有2个人互为朋友，对不对？那你再讲一次你的。因为不知道这个朋友是谁的朋友，这样。对，好，没关系，你知道意思就好了。Alright， 好。Okay, so you can see sometimes it's not easy to write a negation directly, but once we have the help of the Morgan's law to negate the original statement first, then we can translate the English sentence. Okay, so it follows for our previous table because we are talking about when this practical logic is true and when it is false. So it's not easy for you to consider this practical logic. You can firstly translate by the Moore's law to make a solution. Then we can have the corresponding sentences. For this one, once we apply negation, then it will be for all x for some y, not p of xy. That means for every x, we exist a particular y that xy is not true. So you can see, actually, it's just a sentence for every x y, which p of xy is false. So maybe that will be easier for you to consider or thinking the meaning of the negation. All right, let's change. Any question for this section? All right, if no question, then we will stop here. See you 2 days later.